Hi, everyone. Thanks for joining us today. My name is Lorana Ryback. I'm a member of the class of 2011. I currently reside in Washington, D.C. and work for Deloitte in technology consulting for life science clients. I'm also a member of the Alumni Board, which is a group made up of 25 members representing each of the university's schools with the purpose of engaging all alumni and students in a lifelong connection with one another and with the university. Today's session is part of a series that was launched in 2020 called Experience Rochester that exemplifies the university's commitment to lifelong learning. The series features topics and speakers unique to the university. Today, we are joined by Professor Dan Watson and Professor Laura Ackerman Smoller, who will share both scientific and historical insights about solar eclipses. Dan Watson is a professor of physics and astronomy and a laboratory for laser energetics senior scientist at the University of Rochester. His research is centered on the physics of the formation of planets and stars, which he currently studies from space with NASA's James Webb Space Telescope and Hubble Space Telescope, and from the ground with the Gemini Observatory. Laura Ackerman Smoller is a professor of history at the University of Rochester. Her research focuses on areas of intersection between magic, science, and religion in medieval and Renaissance Europe, centering around two major themes: astrology and apocalyptic prophecy, and saints and miracles. At the end of the session, Dean Nicole Sampson will moderate a Q&A with Professors Watson and Smoller. They'll answer as many questions from the audience as time will allow, and you can drop those questions into the Q&A box at your screen at any time. Thanks again for joining us, and I'll turn it over to Professor Watson.
All right, sorry to consume a couple minutes there. Thanks for joining us today. What I'm going to do first, before Professor Smoller gets on to talk more about the intersections, is to describe more about the eclipse experience and the reason that scientists like astronomers, for example, really like eclipses. They are a good connector with the public, and they do represent a formative experience in our civilization. Namely, you can really blame the invention of science on the noticing of the patterns that go with the eclipses. So that's what we're going to do today. The first thing, though, I will point out is my ulterior motive in giving this presentation, which is the QR code that you will see at the bottom of every screen here and up in the one of the corners subsequently, except for the next slide, because just like Robert H. Was wondering, it is worth making sure that your eyewear is up to the task of looking at a partial eclipse. If you follow the QR code, you will get to the AAS, the American Astronomical Society page on eclipse eyewear, and it will tell you how you can tell whether your glasses are good enough to look at a solar eclipse and not damage your eyes. Please don't damage your eyes. Okay, so first, the background here. This is an image that conveys, at least to me, apart from the aircraft, what a total solar eclipse actually looks like. I have seen one, the 2017 eclipse, and I would encourage you to look at this as an immersive experience. That is the experience of the entire cosmos around you, including the shadows and their motion, the inrush of air that comes from removing the sunlight heating of the ground in short order, the behavior of animals as they go into the beginning of nighttime mode, and the excitement of the people around you. At the 2017 eclipse, was aware that far better photographers than I am would be active and would be taking lots of pictures of the event. So I took none of my own. My wife took pictures, but I prefer the wide angle immersive things like that. So that is my advice to Mike T here. My main hint, if you are going to take pictures, is to take a variety of different exposures. A short exposure so that you can see the corona and the ring of fire around the sun, and longer exposures so that you can see the other conditions. This particular image behind Mike's question is a composite of a short and a long exposure, just like that. So if you want, do that, but don't take up time from your experience of the eclipse. You're not going to forget it. You don't need to record it. It will be in your brain forever. Now, a few factoids about Earth, Moon, total solar eclipses. First of all, there are anywhere between about 2 and 5 solar eclipses per year worldwide of all the sorts. The different sorts that we log are total eclipses, annular eclipses, and partial eclipses, by which we mean neither a total nor an annular eclipse anywhere on Earth during any portion of that eclipse. These kinds of eclipses happen in roughly equal numbers. You know, a third of them are total, a third of them are annual, and a third of them never get to total or annular. Total eclipses turn out to happen about 26% more often in the northern hemisphere than the southern, due to quirks of the Earth's orbit and the moon's orbit around the Earth. So you're in good luck there. I suspect that you all live in the northern hemisphere and will have better chances of seeing another one. The upper right-hand picture is a picture of a total eclipse from last year, a long exposure, so that you can see the structure of the corona and some of the prominences around the edge of the disk of the moon, and even Earthshine illuminating the moon in the middle. The lower right is an annular eclipse from about 12 years ago in Arizona, showing that it is still very bright. And that is one reason why in anything but a total solar eclipse, you will be instructed, if you are near experienced people, to keep your glasses on. It is only during the total eclipse portion that that you will hear, if you're in a crowd, an instruction of glasses off. And then just before the moon leaves the scene, an instruction of glasses back on. Now, oops, sorry. Now, at Rochester's latitude, total or annular eclipses occur about 7 times every millennium. So you don't get even one during a long lifetime on the average. So we're kind of lucky that we have 3 solar eclipses, total solar eclipses in 1925, this year, and 2144, which is an answer to Ann M's question here. But we're not as lucky as current residents of Paducah. Paducah lies at the intersection between the track of the 2017 Earth eclipse and this year's eclipse. So they're going to think it's all old hat after a while. Now, our total solar eclipses and our annular solar eclipses are the same phenomenon, and you might be wondering why we get totals sometimes and annulars at other times. And the answer to that is that the moon's orbit around the Earth isn't quite round. It's elliptical, and the Earth sits at the focus of that ellipse, so that part of the ellipse is further away than the average, and part of the ellipse is closer to the Earth than the average. The terms for the maximum and minimum distances are familiar to most of you from reading newspapers and such. The closest approach is called perigee, and the furthest approach is called apogee. That's the maximum distance of moon from Earth, and the minimum distance of moon from Earth, apogee and perigee. So if an eclipse takes place when the moon is near perigee, the moon can cover up all of the sun and more, and that's what makes a total eclipse of the sun. And when an eclipse is not going on, it's what produces a supermoon. If an eclipse happens near lunar apogee, then it can't cover the whole of the sun's disk, and it leaves an annulus of brightness that might be even or might be lopsided, like the picture on the previous slide. That's what we call an annular eclipse, and if an eclipse is not going on, it sometimes bears the term micromoon. Now, these eclipses, I should remind you, are very special. They're very special not just to us, but they're rare in the universe. The reason being that the sun is just about 400 times larger in physical size than the moon, but it also lives just about 400 times further away than the moon. So it's, in angular terms, it's a near perfect size match. That is a rare coincidence. It's unique amongst the 8 planets and their moons. For example, here's the best you can get to approximate an eclipse of the sun by our moon, seen from Mars by the Perseverance rover during an eclipse of Deimos in front of the sun. You can see this is the sun. There's some sunspots and whatnot, but that's as close as you can get to a total solar eclipse that would show the corona and the ring of fire. In contrast, if you went to, say, Jupiter and were standing in the shadow of Io, this is what it would look like. If you were on Sun standing in the, on Saturn standing in the shadow of Titan, this is what it would look like. If you were on Pluto standing in the shadow of Charon, Pluto's not a planet, but it amounts to the same thing. Charon would completely engulf the sun. You would not see the corona. Continuing that thread, it's about an eclipse like ours is about 10,000 times rarer amongst the moons of the planets. They sometimes present each other eclipses, although those only last a few seconds. And the ones that are in which the obscuring moon and the sun are similar in size are 10,000 times rarer than ours. So that's not something that you find in every solar system. It's rare amongst all the solar systems. Now, the other thing that I would like to leave in your mind is that science itself developed directly from systematic logging and observations of eclipses. At first, lunar eclipses, but before the 6th century got going, the 6th century BC got going, it was beginning to be used on solar eclipses. The ancient inhabitants of Iraq, starting with the Sumerians and going all the way through the Neo-Babylonians, kept track of eclipses, and they have rather comprehensive and complete records on lunar eclipses. And by about 700 BC, with a 2,000-year database, they revealed a pattern of lunar eclipses that they began to use to predict lunar eclipses. They knew that eclipses of similar appearance, that is, the same distribution of residual light on the moon, occur every 6,585 days, every 18 years and 11 days. They called the period between these things a sar. And the Greeks adopted that word and gave it a nominative suffix here, and saros is the name that we use for it these days. What I mean by similar is in appearance is similarity in the distribution of light on the moon, or in this case, the sun, and the track through the sky and the elevation at a certain time. Here, for example, is the track of the upcoming eclipse. And beside it on the right is the track of the eclipse 6,585 days previously. And you can see that the track is very much the same, except that it's shifted in longitude. This eclipse is the 29th of March, 2006. These are two eclipses within the same so-called Saros cycle, missing each other only by the 18-year, 11-day lag. Now, as the lunar eclipse lore spread throughout the Near East and Greece and China, although the Chinese got it kind of garbled and it took them a few hundred years to figure out what the Babylonians actually meant, it was realized that solar eclipses of similar size also repeat on the Saros cycle. And nowadays we know that solar eclipses of similar appearance repeat at nearly the same place on Earth on a 3 Saros period. If you go back from the 8th of April this year, 51 years and 32 days, you land on the 7th of March, 1970. And sure enough, very close to the track of the of Monday's eclipse was this eclipse track. That's how good the predictive ability is just on the records of that were available to the Babylonians and the Greeks. In fact, the Greeks drew big attention to this. In Herodotus, we read that of the first very well attested solar eclipse prediction, which was given by Thales of Miletus in the prediction of the 585 BC earthquake. This is celebrated amongst scientists and amongst even amongst science fiction writers. Isaac Asimov often referred to this prediction as the birth of science. Now, there was a battle going on in the middle of Anatolia at the time, and Thales' prediction did not succeed in preventing battle-ending panic. But the fact that this could be predicted and shown not to have required divine agency, it was possible for people to look at eclipses not as something that is a really scary omen, like in the Bible, in Ezekiel and Joel and in various places in the New Testament, but instead to an understanding that nature has predictable behavior that's not necessarily a cause for fear. Here's my favorite example of this from, well, it's in Thucydides too, but it's elaborated in Plutarch's Life of Pericles, in which they were about to go off to invade some country from Athens, and there was a solar eclipse that happened just when they were getting ready to leave. And Pericles calmed the troops by using something he learned from Anaxagoras of holding a cloak in front of the helmsman's eyes and asking him whether that was a terrible omen. And when the helmsman said that he didn't, Pericles asked, and this is a famous quote, "What's the difference then between this and the eclipse, except that the eclipse has been caused by something bigger than my cloak?" That reveals just how much they had learned about the distances in the cosmos and the functions of eclipses in the time since the discovery of the Saros by the inhabitants of Iraq. So this starts a through line in the development of science that leads from Babylon all the way to the Arabic preservers of science in medieval times, at which point Dr. Smaller will take over. I will highlight just my favorite events in this, the career of Hipparchus, who's really the first modern scientist, and about the same time, the construction of the Antikythera mechanism, which was a clockwork with gears and everything that could be used to predict solar eclipses and lunar eclipses. I urge you to Google these things because they make very interesting reading. Now, on Monday, there's going to be a lot more to see at 3:20 besides the eclipse, although I want you to notice the eclipse. The image here is what it looked like to me. This is about how big the corona looked, and one of the things that I found the most striking is that the ring of fire, that is the prominences, the solar prominences sticking out from the sun's surface past the limb of the moon, were very vivid. This photo doesn't really even do that justice. In my eyes, the prominences look bright red with blue cores. I hope I hope we have good prominences, and I hope that looks as vivid to you as it did to me. Now, when we get there, make sure you're sitting someplace that has a clear view to due southwest and halfway between the horizon and the zenith. Very simple instructions for finding it because amongst other things, it's where the sun and the moon are. But if you're going out in advance and wondering where to sit, make sure that you're sitting someplace that has a good view to that direction. Second, do not look at the partial eclipse before and after totality without safe eyewear. Again, if you're wondering whether your eyewear is safe, follow this QR code. Third, when totality begins, take your eclipse glasses off and feast your eyes for 4 minutes on the corona and the ring of fire in the eclipse, and on the things that are nearby in the sky, including the second biggest draw this year in the sky, which is Comet Pons-Brooks. You'll also see Mercury, which I bet lots of you haven't ever seen before, because you have to be looking in exactly the right place at the right time, just before sunrise or just after sunset. And you'll also see some more familiar things like Jupiter and the Pleiades. These things stretched out in order from left to right, starting at the eclipse and going up and left. Ella, who submitted a question in advance, take note of this. It is safe and encouraged to take your glasses off during the eclipse. Just don't do it during the partial eclipse while you can still see strong brightness from the sun. Now here's the scene, and I will finish on this. First of all, noting that you probably want to know more about eclipses, and you will find out more than you ever wanted to know just by Googling Fred Espenak's name. Fred is the leading curator of our lore of eclipses and the leading calculator and predictor of eclipses and eclipse-related phenomena. Second, down here in the lower left-hand corner is your QR code for checking out your eyewear. Lower right is where is going to be the center of your view, where the eclipse is actually happening. And if you move up and left, you first find Mercury. Never mind M74 there, it's too faint. You'll see all these stars, but you won't see the connecting lines between them to indicate the constellations. Then the comet. Comet 12P Pons-Brooks, level in the sky with Jupiter. You won't see Uranus because Uranus is a little bit too faint, but you will see the Pleiades, the fuzzy collection of stars in Taurus that is a prominent feature of the wintertime sky. At this point, I will yield the floor to Professor Smaller, professor of history at the university. And she will continue the story into the medieval times, focusing on the intersections of science and culture and magic and omens and things like that for you. So I will stop the share at this point and enable Laura to join on.
All right, excellent. Thank you so much. So for many people, the phrase, the science of eclipses in the Middle Ages is almost a laughable concept, perhaps best illustrated by a key plot point in Mark Twain's Connecticut Yankee and King Arthur's Court, shown here in our own Rare Books and Special Collections copy of the first edition of 1889. If you know the novel, you know that the novel's hero finds himself mysteriously transported back to England in the year 528. And he's able to save himself from burning at the stake by claiming to be a more powerful magician than Merlin, because he has the power to blot out the sun. He can do this because he knows there was a solar eclipse on June 21, 528, just the day he's set to be executed. So Twain's joke rests upon the contrast that he draws between the knowledge available to a completely ordinary Connecticut Yankee and the barbarous, superstitious minds of medieval Europe. And yet, as I want to show you, medieval Europeans had a sophisticated understanding of solar and lunar eclipses. To be sure, eclipses could figure as portents or omens in the Bible, as Dan just showed, and they did also in ancient Greek and Roman histories. Here you see an illustration of the Book of Revelation 8:12, the sound of the fourth trumpet, at which John learns the third part of the sun will be smitten, and the third part of the moon, and the third part of the stars. The popular 15 signs before doomsday also promised medieval Europeans that one of the signs of the approaching apocalypse would be the sun turning black. And medieval chroniclers certainly larded their histories with eclipses, often portending some future catastrophe or victory. For example, according to the Annals of Magdeburg, those who observed a solar eclipse in October of 1147 concluded that bloodshed was soon to follow. According to William of Malmesbury, when a total eclipse of the sun occurred in England in 1140, it was thought and said by many, not untruly, that the king would lose his power. The 12th century chronicler John of Worcester described yet another total solar eclipse in the year 1133 and added that afterwards, King Henry left England for Normandy, never to return alive. But such examples can blind us to the fact that medieval authors also well understood the science of eclipses. It is instructive to that point to read John of Worcester's entire account of the celestial event he described. He writes, in 1133, a darkness appeared in the sky throughout England. In some places it was only a little dark, but in others candles were needed. The sun looked like a new moon, though its shape constantly changed. Some said that this was an eclipse of the sun. If this is true, then the sun was in the head of the dragon and the moon in its tail, or the sun in the tail and the moon in the head, and the fifth sign in Leo in the 17th degree of this sign. So John accurately describes here the limited path of totality, the changing appearance of the sun during the minutes of the eclipse, and finally, in his strange sounding references to the head and tail of the dragon and a precise location in the zodiac, he alludes to the mathematical theory behind eclipses. To understand this last portion of John of Worcester's explanation of a solar eclipse, we need to enter imaginatively into the medieval cosmos. A picture of the universe, often called the Ptolemaic system, after the 2nd century CE astronomer Claudius Ptolemaeus, whose sophisticated mathematical model of the heavens formed the basis of astronomy up until the time of the so-called scientific revolution. Let's approach this world as a medieval university student might, through the basic textbook of astronomy taught in the schools. Johannes of Sacrobosco's On the Sphere, shown here in a beautiful 1482 edition from Our Rare Books and Special Collections by the printer Erhard Ratdolt, a printer well known for the many mathematical and astronomical works he edited, as well as for the wonderful illustrations he included in his books. As you can see in Ratdolt's schematic diagram, the Earth sat at the middle of a set of nested spheres. So here, there was one sphere for each of the 7 planets, and then on the outside, the sphere of the fixed stars. Now, the planets included all 5 planets visible to the naked eye, so don't expect Uranus, Neptune, or the late lamented Pluto. But they also included the sun and the moon. We see them all here in a beautiful, lovely illustration. The planets are all in blue here. This illustration is on the first folio of a 13th century manuscript, also in the university's collections, of a work called On the Universe by the Parisian theologian William of Auvergne. So here, beginning with the sphere closest to the Earth and the 4 elements at the bottom here, we see the moon, Mercury, Venus, the sun, Mars, Jupiter, Saturn, and then the fixed stars. So, to simplify greatly, movements of these nested spheres explained the apparent motion of the heavens, that is, the changes in the night sky visible from the Earth. Most obviously, the sun, moon, stars, and planets all have a daily rising and setting from east to west, easily understandable as a single rotation of the entire set of heavenly spheres. But the planets all have their own movements as well. The sun, for example, rises half the year farther to the north, half the year farther to the south. This apparent motion was explained by having the sun's sphere turn slowly in the opposite direction from the daily rising and setting motion, that is, from west to east. The result is that the luminary traveled in 1 year's time, roughly, a path circling the Earth, angled from the Earth's and from the celestial equator at an angle of 23½ degrees. And you can see that line here. The other planets each have their own motions. They also move slowly west to east, sometimes north of and sometimes south of the sun's apparent path, all within a narrow band of 12 constellations known as the zodiac. Furthermore, the planets seem sometimes to stop and travel backwards against that slow west to east movement in a motion known as retrograde. And retrograde was explained by a mechanism known as epicycles, but thankfully they need not concern us here. The important motions for us to remember are the sun's 1 year path through the zodiac and the moon's shorter 1 month journey through the same 12 signs. Now, Ptolemy and his medieval heirs also understood that while the sun produced its own light, the moon received illumination only from the sun. The relative positions of the two thus determined whether the moon was full or new, or any of the various stages in between. And that relative position also explained eclipses. As Sacrobosco's charming diagrams here illustrate, when the Earth was interposed between the sun and the moon, shown at the top here, or in astronomical terms, when the two luminaries were in opposition, 180 degrees from one another, the Earth's shadow would block the sun's illumination of the moon and a lunar eclipse would occur. In a similar manner, when the moon stood between the Earth and the sun, or in astronomical terms, when the two were in conjunction in the same degree of the same sign of the zodiac, then the moon would block the sun's light and viewers on Earth would experience a solar eclipse. And the sun looks a little unhappy about that here on the bottom. Now, these oppositions and conjunctions happen once a month. In the case of the sun and the moon, we call them the full moon and the new moon. But as Ptolemy and his medieval heirs knew, we do not have a solar and a lunar eclipse every month. To explain why, let's return to Sacrobosco's sphere. What we see here is the Earth at the center in black, skewered, as it were, by a north-south pole around which the heavenly spheres rotate. Horizontal circles mark out, starting at the top, the Arctic, and then the Antarctic at the bottom, the tropics of Cancer to the north and Capricorn to the south of the equator, and the celestial equator. Intersecting the celestial equator at a jaunty angle here, we see the band of the zodiac with the sun's apparent path marking its center. The reason one does not have a solar eclipse at every new moon is because the moon's monthly orbit sits at an angle to that of the sun. So only when the sun, moon, and Earth are all in the same plane can we have an eclipse. And that lining up can happen only where the moon's orbit intersects the sun's. These movements are shown more easily in this modern diagram in which the sun's apparent path is marked in red with S and the moon's in green with M. The 2 points of intersection, these weird dealy-bobbies here, are the moments when an eclipse is possible. For that reason, the circle that traces the sun's apparent path is called the ecliptic, the circle on which eclipses can happen. And the 2 points where the moon's path intersects that path of the sun were known in the medieval era as the head and tail of the dragon. In modern terms, we call them the ascending and descending lunar nodes. These points also have an apparent motion along the sun's orbit, a path with a period of just over 18½ years. So when our monk John of Worcester wrote, some said that this was an eclipse of the sun. If so, the sun was at the head of the dragon and the moon at its tail, he almost got it right. For the darkening of 1133 to have been an eclipse, yes, the sun and moon needed to be in one of the two lunar nodes, the head or tail of the dragon. But for a solar eclipse, both needed to be in the same node, that is, in conjunction. And I've now checked two manuscript versions of John's Chronicle to see if perhaps there's been some sort of editing error or translation error in modern editions. But I think the mistake must have been either John's or more likely some manuscript copyists. Whoever made the mistake knew the lingo. In fact, knew enough to specify a single location on the zodiac, Leo 17 degrees. But he got a little confused about the conditions needed for a solar eclipse as opposed to a lunar eclipse. Now, such confusion is perhaps understandable if we realize that John was living at a time when works of natural science, largely Greek in origin, that had been preserved in Arabic were beginning to make their way into Latin-speaking Western Europe in translation from the Arabic, revolutionizing Europeans' knowledge of nature. John's contemporary, Adelard of Bath, probably the only person in England at the time capable of casting a horoscope, had read a few works by Arabic scientists, but certainly not Ptolemy, whose major astronomical textbook would not be translated into Latin until 1170, long after Adelard's or John's death. So I think we can cut John and his scribes a little slack. But a half a century later, in 1191, an English monk named Richard of Devizes would ridicule people who didn't understand the world and its workings, and who therefore ignorantly assumed that a solar eclipse witnessed on June 23rd of that year must be some sort of omen or portent. So if eclipses were not just celestial omens, but were rather built into the orderly working of the universe, they nonetheless could serve as signs. In the sophisticated astrological textbooks that entered Europe via translation from the Arabic, medieval natural philosophers learned to look to eclipses in forecasting the weather, as shown here in a treatise by the 14th century astrologer Firmin de Beauval, in another lovely 15th century imprint in our rare books and special collections. Firmin's instructions are quite detailed. Here, to understand the effects of any given eclipse, one must cast a horoscope for one's own location at the time of the eclipse, and then calculate the essential dignities of each of the planets on the chart, as well as consider the location of each of the zodiacal signs. Here, Firmin notes that if one of the signs that represents a wild beast, such as Leo, is in the northern sky, the eclipse's effects would include earthquakes and the destruction of cities, whereas such a sign in the south would indicate strong winds and rain. The phases of the moon could also be among the astrological considerations a good physician would take into account in deciding when to bleed a patient or administer medicine, or even in prognosticating recovery or death. Hence the appearance of full and new moons. In the medieval equivalent of an Apple Watch, this lovely folding physician's almanac, also from U of R collections. But for serious astrologers, solar eclipses were relatively minor events. And the reason is quite simple. The sun and moon were just two of the 7 planets. True, astrologers set great store by conjunctions of the planets, especially for large-scale predictions. But they placed by far the most importance on conjunctions of the 2 superior planets, those farthest from the Earth, Saturn and Jupiter. At best, a solar eclipse could serve to intensify the effects of a Saturn-Jupiter conjunction, such as one did for the Saturn-Jupiter conjunction in 1484, which provided fodder for the runaway bestseller Prognostication by the German astrologer Johannes Lichtenberger, who said that the effects of all these combined celestial events would be felt all the way until 1567. As one of Lichtenberger's later readers added, the foul eclipse portended a brief period of destruction and oppression of the clergy. Or in the slightly hyperbolic phrasing of our Firmin de Beauval, should a solar eclipse occur at the same time as the most important of Saturn-Jupiter conjunctions, one could expect to see effects lasting for 12,000 years. Discussions of eclipses also featured in medieval works of theology. In both theological and astronomical treatises, it was standard for authors to offer an explanation of why the eclipse that was seen at Jesus's crucifixion could not have been naturally occurring, but rather was miraculous. To quote our William of Auvergne manuscript, a true eclipse could not have happened at that time because the moon was full and the moon and sun on opposite sides of the earth, as far as possible from the moment of conjunction. Indeed, as William added, Dionysius, a noted Greek philosopher, seeing the eclipse and realizing it had to have been a divine sign and not a natural event, converted to the Christian faith on the spot. And medieval astronomers and astrologers often elaborated on this point. So, for example, before concluding that the darkness during the crucifixion had been miraculous, the 14th century astrologer Cecco d'Ascoli entertained and dismissed the possibility that a comet might have obscured the light of the sun, that a magical stone called heliotrope might have caused a temporary fog over Jerusalem, or that the planets Venus and Mercury had passed between the earth and the sun at the time. Thus, theologians, physicians, astrologers, natural philosophers, monks, and any person with a smattering of education in medieval Europe understood the theory behind solar eclipses. In that respect, medieval people were much more like Twain's Connecticut Yankee than they were like the ignorant and superstitious medieval folk whom Twain imagined to inhabit King Arthur's court. Medieval people knew the conditions under which the sun could undergo an eclipse, and armed with almanacs, tables, calendars, even folding physicians' guides, they knew how to forecast when an eclipse was going to happen. So the next time you're tempted to poo-poo medieval superstition and ignorance, remember that people in the Middle Ages understood solar eclipses far better than Mark Twain understood people in the Middle Ages. So thank you for your attention. I will open things up to Nicole Sampson, who will moderate a Q&A with myself and with Dan Watson.
Thank you, Laura. And let's first thank Professor Watson and Professor Smoller for very nice presentations. I've had a few questions come in, and I'm not sure who should answer this one. We had a little bit of back and forth in the live chat Q&A about how eclipses were observed in the past. And I think if I was watching carefully enough, there were no pictures shown of the camera obscura. And one of the two of you could comment on when did that first come about and what is it? What is the camera obscura, which predates all of our nice eclipse glasses that we will be wearing on Monday.
You want that one, Laura, or shall I do it?
I give you that one.
Okay. A camera obscura is just a pinhole letting sunlight through. If you make yourself a very dark room and have a window on the sunny side and permit just a small hole to let sunlight through, you will see formed on your floor or your wall an image of the sun. And this, I mean, camera obscura is what they called it in the, I guess, 14th century when it was first invented. Nowadays, we call it a pinhole camera, and it is the simplest optic. It's something that the people over in the Institute of Optics learn about on day one, that if you have a small enough entrance and a distant enough object, you will get an image formed with very large depth of focus on any surface that you put past that little hole. There are sketches of this all over the place, and I have some favorites, but that's probably sufficient answer.
Thank you. So following up on your talk presentation, Laura, you've convinced me at least that the medieval ages, people knew what they were doing. How much of that carried forward into the next, and I know this is not your specific area of historical knowledge, but how much of that carried forward and how much of that knowledge was lost as we progressed, into the subsequent centuries? Was that information added to, or, as telescopes and the like began being developed in the time of Galileo and Renaissance, etc.?
Sure. That's a great question. So if I have two thoughts. One is, if anything, this type of knowledge became even more widespread, particularly with the birth of printing around 1450, because one of the things that was widely printed were almanacs, which included, tables of full and new moons, of eclipses, often included an astrological prediction for the year, a horoscope cast at the moment of the sun's entry into Aries, the beginning of the astronomical year, the vernal equinox, or even if there was an important conjunction happening at the time, a forecast based on that. And then also we have many still surviving, and these would have been quite ephemeral, single sheet broadleafs, broadsides that comment on some celestial events, whether an eclipse observed or some strange portent seen in the sky. But we had an interesting conversation actually in my class on Tuesday. I was talking about Galileo and talking about some of the things he saw with the telescope that made him think the old view of the cosmos wasn't wrong. And one of them was sunspots. And because we've all been thinking about, don't look at the sun until it gets into totality, I sort of muttered, I don't know how Galileo didn't damage his eyes, because he drew pictures of sunspots. And Dan, one of your students, said, well, actually he did. So no, this knowledge became in the Renaissance, the early modern period, if anything, more popularly known and more widely spread.
Yeah, Rihanna told me about that.
So speaking of telescopes, you showed us, Dan, a nice map of the sky and what will appear at the totality of the eclipse with respect to planets. And you mentioned 2 planets that you could still see with the naked eye, but what's needed to see the other planets at that moment of totality? And how does one, and the follow-up is, so this is a 2-part question. How does one protect the telescope in your eyes through the telescope if you happen to swing back towards the sun as it's emerging?
The basic answer is never point a telescope anywhere near the sun unless you're a pro. No, and in any of the parts of the sky that you'd be interested in, that's too close to the sun. If you are looking through it, that would be very bad. You shouldn't even look at the full moon through a good telescope. And even if you're not doing it through the with your eyes, there's a fire hazard. As soon as the sun comes back out from behind the moon, the focused light will start a fire. It will do no harm to your lenses, but it will start a fire someplace else. So please don't do that. There are easier ways to see the things that are in that scene with a telescope. If you just wait until after the sun goes down, you can point any telescope of a few inches or bigger in diameter towards the direction of Jupiter, and you will see Uranus off to the sky, off to the side, for example. So the telescopes, small telescopes, would do a good job on any of this scene, but please don't do it while the sun's up.
Great advice. Thank you for that. And following up on telescopes and some of the beautiful pictures you showed us, how does one go about photographing, capturing this event, or can you? So there's different types of films and detectors and cameras. And again, single lens reflexes, I'm assuming, would be a no-no. So
yeah, don't use an SLR camera. It's better to to have something that has a very, very long focal length, as long as you can get, because the interesting part of the scenery is close by. That is, if you want to take a detailed picture of the moon illuminated by Earth shine and the corona and prominences. The people who do that and make beautiful pictures like that are using, half-meter long focal length lenses and to spread the light out so that it doesn't start a fire, and solid state detectors behind that, like CMOS cameras that are becoming very popular these days. For the very wide angle views, like the one that I showed right at the beginning, that you can use an SLR camera for, because in that sense, you're not going to be interested enough to burn a hole in your detector by letting the shutter still stay open when the sun is peeking out. So those were taken by with SLR cameras, except that great care was taken only to have the shutter open, or the sun, or the thing pointing in the direction of the sun, while the sun is behind the moon. The long focal length cameras, they can leave tracking the sun, but the people who are taking these photos will divert their SLR cameras away from the sun's line before the sun comes back out.
This is a highly technical undertaking, so do more homework before trying this at home, is what it sounds like. We have a question about behavior changes of animals, humans, maybe plants. I don't know if plants get confused during and after an eclipse of this magnitude. So what was known in the medieval ages and what is known now? Has it changed? And what happens in that moment?
So it's interesting in discussions of prophecy and whether natural prophecy, or whether prophecy is, or predicting the future is available by natural means. It is quite commonplace for medieval theologians and natural philosophers to point to animals having sort of a natural instinct of what's happening in the future, and that they can sense somehow that something's happening. For example, that an eclipse is going to happen is one of the examples that medieval authors will point to. It's interesting. I'm trying to think of chronicles that describe eclipses, and maybe this is a little bit the anthropocentric bias of a medieval chronicler, but they're much more interested in human behavior at that particular moment, than in animal behavior. But there was this sense that animals can sense things.
Interesting. So I think we're at time. So I wanted to give each of you 1 minute approximately to say any final words or thoughts you'd like to share with the audience today. Laura, do you want to go first?
Maybe I'll just give a reading assignment or a reading recommendation. And I'm not plugging my own work. I just wanted to recommend, if people want to know more about the fact that people in the Middle Ages actually had quite sophisticated knowledge of nature, I would recommend a book published a couple of years ago by Seb Falk called The Light Ages. So instead of the Dark Ages, The Light Ages, The Surprising Story of Medieval Science. It's a wonderful book, and it's a really good read, and it ends with a description of a very sophisticated astronomical instrument, reminiscent of what you were describing, Dan, but from the 14th century.
Thank you. And maybe one of our behind the scenes moderators could put the title of that book in the chat for the audience. Dan, final words.
I I would like to pass final words back to Laura. I've been answering questions in the chat as we've been going on, but there's one question left from Robert H. again in the Q&A for Laura, wondering whether that pendant is an annular eclipse.
What was the artist thinking when they made your necklace? That's what the audience wants to know.
I thought, well, it's the closest I had. I thought it might be a crescent moon. It's possible it was made by an Islamic artist in Africa. I bought it in Africa, but it was the closest thing I had for the day. But thank you for noticing.
All right, on that note, I am going to turn it back over to Lorana. Thank you.
Thank you, Nicole, Dan, and Laura, for that engaging and informative conversation. The interdisciplinary nature of this discussion just highlights the uniqueness of the University of Rochester's curriculum and research. So thank you for bringing those different parts of the university together. And thanks everyone for joining us today. I hope that you enjoyed the program, and I hope that we get to see you at future university events. Have a great rest of your afternoon, everyone. Bye.